Welcome to Unit 12. In this unit, we are going to be talking about the Big Bang Theory. In this unit, I will be emphasizing the development of the hypothesis, the predictions of the theory, and the evidence for the theory. So those will be our three mini lectures. In this first one, I'll tell you about where the Big Bang Theory comes from, how it was developed, some of its basic predictions that have been shown to be true. In our second mini lecture, I will give you a history of the universe, which relies heavily on particle physics. We won't go too deeply into that, but I want to show you some of the predictions that have been made and let you know where they've been tested and where they haven't. In our final mini lecture, we will go over some of the tests of the Big Bang Theory and the related theories of cosmology. In our last unit, we talked about the cosmological principle. And we discussed how the cosmological principle, which says that the universe is more or less the same on big enough scales and the same laws of physics apply everywhere. We also saw how there's an expanding universe, and we've talked in the last couple of units about how there is a finite speed of light. And that led us to these implications. First of all, the universe is changing, has always been changing, and will be changing. Second, when we look further away, we are looking into the past. And third, in the past, everything had to be close together, and if you run the clock backwards, and physics theories do allow you to run the clock backwards to see what happened, we find that 13.7 billion years ago, everything was in the same spot, which meant that the universe had a definite beginning. So let's think about what happens going backwards. In the next mini lecture, we'll talk about what happens starting at the Big Bang and going forward, so we'll cover this again. But let's just think, if we made the universe get closer together as it was in the past, then the early universe was much denser. And we know that when gas is denser, it gets hotter. Further, we know that if gas gets hot enough, the hydrogen ionizes, that means it loses its electron, and that creates a fog that's difficult for light to penetrate. We can see this in the sun. The sun's hotter than 4,000 degrees and we cannot see through it. If we make this gas hotter and denser yet, then nuclear fusion can and will happen, and that's what happens in the center of our sun and other stars. And even hotter and denser, atoms can break down into component parts, and this is something we do in particle accelerators. So these things have all been tested, and if we run this expanding universe backwards, then we can think that all these things happen in reversed order. So in 1925, a Jesuit priest and physics PhD named Georges Lemaitre, he was a Belgian scientist, he proposed that the universe began from what he called a primeval atom that exploded. So this is before Hubble's law was certified, but it was already known that some of the spiral nebulae were heading away from us. And so Lemaitre proposed that if you had this very dense state of matter and it exploded outward, it could create a universe like what we see. And here you see Lemaitre meeting with Einstein. Lemaitre was a big proponent of Einstein and recognized the implications that an expanding universe meant that in the past everything was close together. Other astronomers at the time didn't like this, and one reason they didn't like it is because they had a view that the universe was eternal and unchanging. One of those astronomers was named Fred Hoyle at Cambridge, and he dismissed this idea, and in the 1950s he says the universe could not have formed from some big bang. And that's where the name came from, and it stuck. And it was meant to be derogatory, but that's now the name that we use. Now, when people began to think in earnest about the Big Bang hypothesis, they realized that there were three key predictions. One of these is that the universe should be expanding, and that's from Lemaitre's original work, to show that the universe should be expanding, and it should expand according to a relation now called the Hubble law. And Lemaitre predicted this in 1925. Hubble published his work on the Hubble law in 1929. So the prediction came first, the discovery and confirmation came later. In 1948, physicists working on the Big Bang hypothesis realized that after the Big Bang, conditions would have been very conducive to nuclear fusion. It would have been hot and dense. And by calculating how fast the universe would have been expanding, how hot it would have been, how dense it would have been, they estimated that the universe should be 75% hydrogen, 25% helium. That was actually already known. Cecilia Payne-Gaposchkin had figured that out in the 1930s. But this was the first hypothesis that could explain why you had those numbers. But further than that, these predictions calculated that there also would have been trace amounts of other rare elements formed during this nuclear fusion of the Big Bang, such as deuterium. Deuterium is a proton plus a neutron, so it's a form of hydrogen. If you've heard of heavy water, it's because that is where you have oxygen with a deuterium atom instead of just a hydrogen atom attached to it. The amount of the universe that would be deuterium is very small, 0.01%, but in fact, that's what we measure. The most recent good measure of deuterium was made in 2005 and confirmed this prediction. The third prediction that the Big Bang hypothesis made was that the very early universe would have been so hot and dense it would have been a black body. In fact, it would have been a perfect black body. The light from that black body should still be visible, and the temperature of that black body as viewed now would be a few degrees, because as the universe expands, it also expands the wavelengths of the light, and so it shifts that peak wavelength from the very hot temperatures, short wavelengths it would have been, down to the long wavelengths that correspond to a few degrees Kelvin. And this was predicted in 1948. It was nearly 20 years later that two engineers, Arno Penzias and Robert Wilson, were building a radio telescope. Here's a picture of their radio telescope. It looks like an ear trumpet that some poor deaf person would be sitting in that little shack so they could hear. But it was a radio telescope meant to receive microwaves, and their reason for building it was for communication. Our cell phones today use microwaves to communicate, and this was some of the very early attempts with that technology. But what they noticed was that it didn't matter where they pointed their antenna, they were picking up some background noise, some hiss, and they were looking for the source of this noise. They considered that their electronics weren't right, so they replaced it and redesigned it several times. They still got the noise. There were a lot of pigeons that liked to roost in this antenna, so they were constantly scraping out the pigeon dung and scaring the pigeons off and washing it down just in case that had anything to do with it. Didn't make a difference. They noticed that what they were getting was a signal similar to a black body with a temperature of about 3.5 degrees Kelvin. Penzias and Wilson contacted some physicist friends because they'd heard some of them talking sometime about maybe the universe would have light of a few degrees Kelvin. And they went to Princeton and they presented their findings. They talked about all their work. And these Princeton astronomers and physicists turned to them and said, "You've won a Nobel Prize." Because they had discovered microwaves coming from the universe that are an echo of the Big Bang. And 13 years later, they won the Nobel Prize in Physics for this discovery. This is called the cosmic microwave background because it's microwave radiation. That's where the peak of your black body is for 3.5 degrees. Cosmic because it comes from the universe, and background because it's from every single direction. The plot on the left shows the results from a satellite launched in the early 1990s called COBE. And the individual points here are measurements of how much light is coming as a function of frequency, which remember frequency is related to wavelength. And the line is not a fit to the data, but is a prediction for a black body with a temperature of 2.725 degrees Kelvin. And you see that the points fall right on the line. Data doesn't get any better than this. This is a perfect black body at just the right temperature. On the right, there are some different views of the background. We'll come back to these views in the third mini lecture. It's important at this point to emphasize there has never been any other scientific hypothesis for the origin of the universe that made so many predictions that were later tested and found to be true. And that's why the Big Bang is no longer considered a hypothesis, but is considered a theory, a well-tested bit of science that explains a large part of the universe and that has passed every test it's been put to. So the three predictions we've covered so far: the expanding universe, that was the original prediction, and Hubble discovered that was indeed true. The abundances of elements, and especially of this isotope of hydrogen called deuterium, the predictions and calculations were made in the 1940s, and direct measurements are still being made that match these abundances. And finally, this cosmic microwave background radiation, an echo of the Big Bang. We'll talk in the next mini lecture where it comes from. That was predicted in the 1940s and discovered in the 1960s. There have been many other predictions by the Big Bang Theory since. We'll talk about some of those in the next mini lecture. And some of them have required a few revisions to the theory, though none of them have been fatal. And as I say, no other hypothesis, even new hypotheses being put forward today, can match all of these observations about the universe. And that's why astronomers are so convinced that the Big Bang is an excellent theory. It just explains such a large fraction of what we see in the distant universe. So if you want to try and overturn it, you need to put forward a scientific hypothesis, a testable idea that explains what we see and makes new predictions that the Big Bang Theory doesn't. So that's our discussion of the origin of the Big Bang hypothesis, the major predictions that were found to be true and so led to the Big Bang now being considered a theory. In our next mini lecture, we will go on to a history of the universe from the Big Bang up until the present.